It's 14. We can start. So yesterday we looked at two theorems, which we use to find these Laplace transforms. So we had theorem 1, which we called the first shifting theorem, or if you want, the S shifting theorem, because there's a shift in the S variable. So what did we say about, what does this theorem state? So it states that if the Laplace transform of f of t is equal to f of s, then the Laplace transform of EAT f of t is f of s minus a. So this shouldn't confuse you. So this small letter f of t is exactly this one. What has changed here is that you're not only finding the Laplace of f of t, you're finding the Laplace of the product of f of t and this. So this theorem says if you know this, if you know the Laplace of this function f of t, then it's easy to get the Laplace of the product of the exponential and this f of t. It's just this function shifted by a. So instead of s, you have s minus a. So this big F is exactly the same as this one. And the second theorem is going to follow in a similar manner. And this we called differentiation of transforms. And the transforms we're talking about are the Laplace transforms. So similarly, if the Laplace of f of t is capital F of s, then the Laplace, if you multiply this function by t to the n, f of t like this, then the Laplace of this is -1 to the n, and then f, the n derivative of this function. So again, this f of t is exactly this. Here I'm finding the Laplace of t to the n multiplied by this function. So if I know that the Laplace of f of t is f of s, then the Laplace of this product is going to be this. So this is -1 to the n, and this is the nth derivative of this function. And your derivative here is with respect to s. So,
excuse me, sir. I came a little bit late, so I would like you to repeat the theorem, the first theorem there. I didn't get it.
but we did it yesterday also. Did you get it yesterday?
No.
So, okay, to explain, let's do some bit of examples, then it will become clear. If it doesn't, then you can ask. So I was just doing a recap of what we did yesterday, and we do some examples on the same. So the examples that are following: find the Laplace transforms of the following functions. Of the following. So the first one, f of t, small letter f of t, is say e to the 5t, and we're multiplying this by
Oh, yo. Yeah, kaka school. Zina.
Please mute everyone.
Okay. Everyone is muted. So the other one is e to the, say, negative 3t, and then cosine of, let's just say t, right? So solution. So typically, when you see this function, this applies theorem, the shifting theorem applies specifically on such functions. So you've got the product of the exponential and some other function. And the goodness about this other function is that you know its Laplace, same as the second one. So if we look at the first one, we know the Laplace of sine negative 2t. What is it? Who can tell us what the Laplace of this is? No one?
Negative 2.
It's what?
2 over a squared minus a squared, which is a minus 4.
Okay, so it's going to be s squared plus minus 2 squared like this. So it's going to be, so this just becomes 4. So it's minus 2 over s squared plus 4. So this is the transform. So the S-shifting theorem says if you know the Laplace of this, then it's easy to get the product of this. You don't have to start integrating. You don't have to go to the basics of using the definition and integrating the whole function. So it says that since you know the Laplace of this, the Laplace of E. So let me do this before I even write that. So this is my f of s in the theorem. So this is my minus 2 s squared plus 4 is my f of s. I'm shifting my a is 5 here. So if you find f of s minus 5, it's going to be minus 2. So that means in place of s, you put s minus 5 over s minus 5 squared plus 4. And this is the Laplace of this transform. So I can now write that the Laplace of E5t sine negative 2t like this is f of s minus a. A is 5, so it's f of s minus 5, which is this negative 2 over s minus 5 squared plus 4. Comments? What do you think?
May you kindly show the previous page?
Okay.
Is that 5 or s in the question?
This, it's 5.
All right.
Yeah.
Thank you.
Should have written it properly. So the second one, again, applying the S shifting. So in this case, your G of t is E minus 3t cosine of t. So again, this is a product of the exponential and this function, cosine of t. We know the Laplace of cosine of t. Laplace of cosine of t is s over s squared plus 1. So if we know this, then we can easily get the Laplace of this product by applying the S shifting theorem. So how do we apply it? F of s in this case is this Laplace, which is s squared plus 1. Our a is -3, so s minus a will be s plus 3. So f of s plus 3. So it's this function, in place of s, we put s plus 3, so it becomes s plus 3 over s plus 3 squared plus 1. And the theorem tells us that this is the Laplace of this product. So therefore, the Laplace transform of e minus 3t and the cosine of t is s plus 3 over s plus 3 squared plus 1. So this is 1 squared, which is 1. Any questions on this example?
So,
Yes.
is it possible? I don't know if this will make sense, but you cannot like separate the exponential and the trigonometric function, the e cos, and have the separate. It's not done that way. It can be done that way.
No. So what you're saying is we want to find the Laplace of e minus 3t cosine of t. And you're saying we should get the Laplace of e minus 3 of t.
Yeah.
And then the Laplace of cosine of t?
Yes.
No.
Just okay.
These are not equal. So you can't distribute it over a product. If it was Laplace of e minus 3 of t plus cosine of t, that's why we say this Laplace transform is a linear operator.
Okay.
So,
okay.
So this becomes Laplace of e minus 3t plus the Laplace of cosine of t. So this is fine. If this was minus, it's still fine. But product and quotient, you can't do that. So that's why we need that theorem. And the reason you can't do that is the same as integration. You can't distribute integral over a product, right? No wonder we use, what's that rule? No wonder we do it by parts. Whenever you have a product, yes, you do integration by parts, because you can't just say you have u and v, then you say the integral of u multiplied by the integral of v. No. Okay, good question. Any other questions? No. So I want us to do some examples on the other theorem, differentiation of transforms. So I'll call this example 2 for today. So find the Laplace transforms of 1 cos f of t to be t, then the hyperbolic sign of t. And the second one, g of t to be t squared, then hyperbolic cosine of t. So this is a product of a polynomial, in this case t to the n. Our n is 1 multiplied by a function whose Laplace transform we know, so we can apply the theorem on differentiation of transforms. So solution. So this is my f of t, hyperbolic sine of t. So I need to first check the Laplace of this. So Laplace transform of the hyperbolic sine of t is equal to, so it will be 1 over s squared minus 1. And this is your f of s that appears in the theorem. So this is 1 over s squared minus 1. So the theorem says, if I can just restate it here, a short form of the theorem. So if n is equal to t, then it says t f of t is equal to negative f prime of s. So I need to find the derivative of this function with respect to s. So f of s is equal to, and I'll rewrite it for the purpose, so I can use the quotient rule. Or if I want to avoid that, I can use the chain rule. So using the chain rule, I'll write it like this: -1. And so f prime of s will be, I drop the negative, so -1. And if I drop the negative, -1 multiplied by s squared minus 1 to the power -1 minus 1, which is -2. And then I differentiate what is inside, and it will be 2s. I multiply by 2s. So f prime of s is -2s over s squared minus 1 squared. So going back now, I found my derivative, just need to multiply it by negative, then it gives me the Laplace of this. So therefore, the Laplace of t, hyperbolic sine of t, is 2s over s squared minus 1 squared. Any questions?
Why the negative has disappeared?
Yes, so this negative has disappeared because I've multiplied it by, you have to multiply it by this negative. So this is f prime of s multiplied by this negative, then it becomes positive.
Thank you.
Good.
Also, what about if the t was t squared or any t to power, let's say any power, for example? How do we have sorted it out as well?
Yeah, so the theorem is, the general one is t to the n f of t is equal to -1 to the n f of f to the n of s. So when n is 1, like in our case, so t to the 1, which is just t, -1 to the 1 is negative, and this becomes f prime of 1, like the first derivative. If it's 2, then this becomes t squared. -1 to the 2 is 1, so it becomes 1, and this becomes f double prime s. Right?
All right, thank you, sir.
So in doing the second one, and it's related to the previous question, our g of t is t squared, then the hyperbolic cosine of t. So just to restate the theorem, f t to the n f of t is equal to -1 n Fn of S. In our case, n is 2. So when n is 2, what do we get? We get that the Laplace of t squared f of t -1 to the 2, which is 1. And this becomes f double prime of S. So we need to get the Laplace of the hyperbolic cosine. And this we know is S over S squared minus 1. And this is our f of S, which is stated in the theorem. So we need to get the second derivative of this. So start with the first derivative. What's the first derivative? So here I'll be forced to use the quotient rule. So the quotient rule goes like, so this is uv, so I start with u prime. So the derivative of s is 1. So I'll just write 1. I keep this, so it's s squared minus 1 minus, I keep this, so it's s, then I get the derivative of this one, which is 2s, my v. So it's 2s over v squared. So it's s squared minus 1 squared. That's the first derivative. Let's simplify it. So this will be s squared minus 1 minus 2 s squared over s squared minus 1 squared. So f prime of s is s squared minus 2 squared gives me minus s squared, then minus 1 over s squared minus 1 squared. That's the first derivative. We're not done. We need to get the second derivative. So second derivative, again, using the quotient rule. So it's f prime of s is going to be, so this is our u, this is our v. So u prime is going to be negative 2s u. Our v is s squared minus 1 squared, then minus, what is our v prime? So I notice I ran out of space here, so I abandon this and I write it. I start from here. So this is f prime of s is negative 2s, and then s squared minus 1 squared minus, then the next thing is we keep u constant, so u is negative s squared minus 1, and then we get the derivative of v. So the derivative of v, which is in the denominator, is we drop the 2. 4s.
Yeah, it'd be 4s and then s squared minus 1.
Okay, okay, I see it. Okay, let's do this. So it will be, we drop the 2, so it multiply by 2 s squared minus 1. So we drop the 2 and then we do what is inside, chain rule. So what is inside will give us 2s. Yes, so it's 4s squared minus 1, as you said. Very good. And the denominator squared is s squared minus 1 to the 4. Okay. And so we can just simplify things. So this is actually the Laplace. Let's just simplify things. So what can we do? We have s squared minus 1 here, s squared minus 1. So I think we can factorize. So it's s squared minus 1. Factorizing, what do I remain with here? I remain with minus 2s, then s squared minus 1. And then what do I remain with here? I remain with minus 4s. Yeah, 4s. Then minus s squared minus 1. Yes. So everything over squared minus 1 to the 4. So this becomes f prime of s will be, so s squared minus 1 here. So we're going to remain with 3 there. Cancel 1. Then just to open the brackets there, we're going to have negative 2s cubed, then plus 2s, then minus plus actually 4s cubed, then plus 4s over s squared minus 1 to the 3. So f prime of s is, like terms, 4s squared minus this remaining 2s cubed, and 2s plus 4s is 6s over s squared minus 1 to the 3. Therefore, the Laplace of t squared and the hyperbolic cosine of t will be 2s cubed plus 6s over s squared minus 1 to the 3. That's how we apply this theorem. Any questions?
Sorry, sir, can I take a look at the previous page?
Yes. Yes.
So, sir,
Yes.
in an exam, we're going to state which theorem to use for each question, or maybe you just choose.
You just go direct. There are very few theorems, so it's obvious which one you're using. So you don't need to state. It's not as if the examiner won't tell which one you've used. Has your question been answered? Are you happy with the response?
No, sir, I was actually like asking if you give a question in an exam, we're going to state like for us which method to use to answer that question.
Which method? What, by method you mean what?
Which theorem?
Yeah, so I answered to say you just have to write directly. You just have to show all you're working. You don't have to say, okay, here now I'm applying S shifting or differentiation of transforms. It's not necessary because there are very few theorems, and whenever you use one, it's obvious which one you're using.
Okay, sir.
Yes.
Like, do you ever ask questions where you're told to derive a Laplace transform, for example, the cosine of a sine or a hyperbolic cosine?
No, we don't. So we expect those are like our basic, maybe not call them identities, but those ones we expect that you know them. Everyone knows them. They are standard, and you just use them. Like for example, here I just wrote Laplace of hyperbolic cosine of t is this. Even in your exam, we just expect that you write this. You don't have to derive it, and you'll never be asked to derive it because there are going to be more challenging questions than you recalling how to derive the Laplace of a basic function.
Okay, thank you, sir.
Okay, so if you don't have any questions, then we do some examples. So we've done, the previous examples were on finding the Laplace. The next example is on finding the inverse Laplace. But you can also apply those theorems when finding the inverse Laplace transform. So example, find the inverse Laplace transform of, so we've been given a function, let's call it big F of S is equal to 3s minus 2 over 2s squared minus 6s minus 2. So this is the function. So how do we go about such a function? Yeah. So like I said yesterday, we have to first look at the denominator, try to manipulate the denominator, then it will give us an idea of how we should manipulate the numerator. So if I just take the denominator, which is 2s minus 6s minus 2, 2 is common in all these terms, so I can factorize my 2 so that I have s squared minus 3s minus 1. And then I can complete the square. So I'll say 2, this becomes 2, then s squared minus 3s. So completing the square, I will say the half of this -3, so I'll say plus -3 over 2 squared, and then subtract the same, so minus -3 over 2 squared, and then minus 1. So this is going to be 2. Then this is a complete square, so it's s minus 3 over 2 squared. This is minus 9 over 4, and then minus 1. So this is 2s minus 3 over 2 squared. -9 over 4 minus 1 will be -13 over 4. So that's my denominator. So if my denominator is like that, then it gives me an idea of what I should do to my numerator. So therefore, f of s is 3s minus 2. So let me write 3s minus 2 over 2. Then s minus 3 over 2 squared minus 13 over 4. Let's include the brackets like this. So because I have s minus 3 over 2 in the denominator, I need to have it in the numerator, because the plan is to use the s shifting theorem. So this is, let me first factorize the 3. So it's 3, then s minus 2 over 3 over 2. And this is s minus 3 over 2 squared minus 13 over 4. And so to achieve the 3 over 2, what I do is I say my numerator will be s, minus 3 over 2, and then plus 3 over 2, and then this term minus 2 over 3 over 2 s minus 3 over 2 squared minus 13 over 4. Okay, so now this will be, we have the 3 over 2 there, so it's going to be, s minus 3 over 2, so it's going to be 3s minus 3 over 2, like this. And then I'll multiply the 3 by this term, so it's plus 9 over 2 minus 2 over 2 s minus 3 over 2 squared minus 13 over 4. Okay, then just to get the difference here, so it's 3s minus 3 over 2. This will give me, so it will be 13. 9 minus 4 is 5, so this will be minus or plus 5 over 2. 5 over 2 over 2, then s minus 3 over 2 squared minus 13 over 4. So this is your f of s. Okay, so we are almost there. So I can write in terms of two terms. So this becomes f of s is equal to, so this will be 3s minus 3 over 2 and divide by 2s minus 3 over 2 squared minus 13 over 4 plus 5 over 2 divided by 2s minus 3 over 2 squared minus 13 over 4. This. Okay. So this is our this is our f of s. Why did we do all this work? Because we want to use the s shifting theorem. So now that we have it in this, we are ready. So we can say the Laplace inverse of f of s is going to be Laplace inverse of this term and Laplace inverse of this term. So let's start with this one. What do you think is the Laplace inverse of the first term? Anyone?
E to the power negative 3 over 2. Oh, sorry, e to the power 3 over 2. T.
Yes, so it's equal to e to the power 3 over 2t, and then
we have cos.
Really?
Hyperbolic cos.
The hyperbolic cosine, because we've got a negative here. So it's the hyperbolic cosine. Okay, continue.
Root 13 over 4t.
So it's root 13 over root 4, which is 2t. Correct. But we just don't forget this 3 and the 2. So we can write 3 over 2 here. Okay. And the second term,
E to the power 3 over 2.
So it's e to the power 3 over 2t. Continue.
Hyperbolic sine.
Hyperbolic sine of what?
Root 13 over 2.
Root 13 over 2t. You just have to take care of the constants. What would be the constant here?
One over 2.
Isn't it 5 over 4?
5 over 4.
No.
So for the hyperbolic sign, doesn't the constant in the denominator have to be the same one with the one on top?
Yes, yes. So good. So what we can do is we can multiply this by root 13 over 2, and here same, root 13 over 2, right? Yes. So you include this, you also bring it there. So I hope enough space. So root 13 over 2. So once you do this now, it gives you an idea of what your denominator is going to be, because this goes with this, so this is remain with root 13, so it's going to be 5 over 2, then root 13. And this is our inverse Laplace.
There's another 2 there.
Which one?
In the denominator and in the numerator. So I think it's 4.
So these 2 and these 2, they cancel.
Oh,
so this
okay.
2 is,
Okay.
yes.
Okay.
So what do you think about this? Is it complicated? Is it too much work?
Very much.
So
Could you show the previous page as it transitions
before
to this new page?
before you go to
Just raise it so that you could show the other page as well.
Okay, so like this.
okay.
Like this?
So I wanted to clarify on the same thing my colleague asked on the 2.
Yes.
How come it's not 4?
So how come it's not 4?
Yes, sir.
So down here, look at, you've got these 2. This is 2 multiplied by root 13 over 2. So the 2's will cancel, just going to remain with root 13.
Yes,
then
sir.
up here you've got 5 over 2. So it's 5 over 2 multiplied by 1 over root 13. That's why you're getting this. This is consumed in the inverse.
Oh, okay.
Root 13
All right.
over 2 is consumed in the inverse, yes.
All right. Thank you, sir.
Okay. Yes.
I've seen something in our calculations. I want to clarify on how you did your arithmetics. After calculating where you're finding 9 over 2, just where you're displaying the picture, I'm finding 5 over 2. So I think that affects our solution.
Okay, here, yes. So where we're finding 9 over 2, this one?
Yes, I don't know if it's something that I'm doing wrong, but I'm finding 5 over 2.
Yes, the origin, when you do the thing, you get 5 over 2, which is this one here. So this is 9 over 2 minus 2, which is 5 over 2.
When I'm bringing them, then I'm subtracting the minus 2 after I get 5 over 2.
So are you getting this, or you're getting minus 5 over 2?
Sorry, let me function.
I guess he's saying instead of having 9/2, we are supposed to have 5/2. I don't know if I got him correct.
No, it's 9/2 because it's 3 multiplied by 3/2, which is 9/2. Then 3 multiplied by -2/3 is -2. So just check properly if on this side everything looks correct.
Yes, but okay, maybe okay. Let me go through.
Okay. So so once you get used to these things, it won't be too much work. So I've got a meeting at 15. So I suggest we do one more example and then call it quits for today. So example is find the inverse. Again, Laplace transform of, let's use another letter. Capital H is S plus 7. And by the way, all these examples I'm getting from the notes. So I posted some notes last year on Laplace and they're still online. I think we can stick with the same. Though we need to add something, then I'll let you know. So, and there's also a tutorial sheet. So you can also make use of that tutorial sheet. So we have this. Now I want to find the Laplace. So it would be tempting to, you look at the denominator, you start completing the square, which is also correct. There'll be nothing wrong with it. However, we notice that this denominator we can factorize, because if you use the high school, if you just look at this as a quadratic, then the product is -10. Then the sum is what? -3. So what are my factors? Two numbers which should I multiply will give me 10, and this add will give me -3.
-5 and 2.
-5 and 2. So this h of s is s plus 7 over s minus 5 and s plus 2. Okay. Then what do? It's a product. We can use partial fractions. We can decompose into partial fractions. So if you remember your partial fractions, you've done partial fractions before, right? Somebody to say yes?
Yes, sir.
Yes.
Good. So decomposing this into partial fractions, what we do is, so this is equal to A. We need to find what our A is, S minus 5, then plus B over S plus 2. Yes. So common denominator, we get S minus 5, then S plus 2. So we get A, S plus 2, then plus B, S minus 5. Equating this to this, we get the following. So the denominators are the same, we just need to cut the numerators. So A is plus 2, then plus B, S minus 5 is equal to S plus 7. So we want to find what our A and B is. So we can say let S be equal to 5. And why do we do that? Because when S is equal to 5, S minus this becomes 0. So that you just remain with that term. So in place of S5, so it's 5 plus 2, 7. So it becomes 7A plus, or is equal to, sorry, plus 0 is equal to 5 plus 7, which is 12. Therefore, A is equal to 7/12. How about B? How do we find B?
Sir, haven't
Sorry,
you
sir,
swapped?
isn't it? Oh,
Haven't I?
I'm saying, haven't you swapped the values? Isn't it supposed to be the other way around? The value of
Oh,
A.
yes. Yes. A is 12/7. I'm sorry. Thank you. If S is -2, and why do we choose -2? Because it will make this 0. Then -2 minus 5 is -7. So -7B is equal to -2 plus 7, which is 5. Therefore, B is equal to 5 -5/7. -5/7, yes. Therefore, h of s, which is s plus 7 over s minus 5, then s plus 2 is equal to A, which is 12/7, divided by s minus 5, and B, which is -5/7, divided by s plus 2. Therefore, the inverse Laplace transform of h of s will be, so what's the inverse Laplace transform of the first term? Anyone to tell us?
(12/7) e to the power 5, is it? E to the power 5t.
Yeah. Yes, so it's 12/7 e to the power 5t. And the second term?
Minus 5/7 e to the power -2t.
E to the power -2t. Yes. And this is our inverse Laplace. Is this okay? Any questions?
So,
Yes?
so
Yes, yes, go ahead.
if we're to complete the square, will we end up getting the same value?
Yes, 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 yes. I'd say yes. Try it. You should get the same function.
All right, so.
Yes. So notice that because you're going to complete the square, you're going to get a function in terms of the hyperbolic and either hyperbolic cosine or hyperbolic sine. And you know that, you know the definition of your hyperbolic cosine. It's equal to e to the t plus e minus t over 2. Then the hyperbolic sine is e to the t minus e to the minus, yes, something like this, yes. So if you use this, it will give you exactly this. You get it, right?
Yes, sir.
Okay. Good question, very good question. Okay. If there are no questions, then we can end here. So some more examples. So what is remaining is we also need to find the Laplace of the unit step functions. That is for those who want to study ahead. Laplace of unit step function. We also need to get the Laplace of derivatives. How can you get, given f of t, are you able to tell, if you know the Laplace of f of t, are you able to tell what the Laplace of f prime of t is going to be? Then we're going to use Laplace to solve differential equations, and then we'll be done. So no questions, we end the meeting. So we're not meeting on Friday because there's a test, and I'll post it soon, maybe tomorrow, but you'll only be able to see it on Friday. And then, yeah, we'll see what we can do after that. So thank you. I'll end this meeting here. I'll share the recording immediately.